So when you have a question related to, okay, write the k nearest algorithm or explain the k nearest neighborhood algorithm. So there could be certain steps that you have to write, and then you can consider an example and you can answer accordingly to the given question. Okay. So when I consider the algorithm of KNN, I'm just going to write it few steps over here. So algorithm of K and M is you have a training phase, you have a training algorithm and a classification algorithm. When it is a training algorithm, it is very simple, where it tells for each training example, okay, there could be a training example called as x comma f of x. For each training example, okay, add the example in the list of training samples. It's like if I have to have a new data that is coming into picture, okay, that new data basically you will consider the training data, complete training data that you have, okay. So, and this will be your training data, and when I have a new data set, that forms my testing data, but I'm going to apply it to the given problem statement such that I will either classify that given point to any of the class categories. It can be any of the categories. So it is telling any example, for each training example, add the example to the list of training examples. So this is my training data. The first one, okay, let's correlate this algorithm with our example so it makes us more clear to understand. What did we do in our example? We had 4 test cases, right? Type 1, type 2, type 3 and type 4. So what I do is my training data, I first get type 1, I write it over here, I calculate the Euclidean distance with respect to test data, okay. Type 2 again, I add it over here, type 3 here and type 4. So which means each and every data sample that I'm going to consider is going to be within my training data. It's just a very simple one, but a notation given to that is more important. Any data, any training data or any data point that I encounter is actually going to be added into my training data. Very simple as that. When I come to the classification algorithm, what does your classification algorithm do? Suppose let me consider a given instance of xq to be classified. So this is my test data that is given, and the test data I'm going to represent it by xq because I'm going to perform an operation on it, right? So this is my query instance. So xq is a query instance which is nothing but 3, 7 in my example. Okay, so that is xq. And from there what I'm telling, let x1 to xk denote k instances. X1 to xk is basically the instances x1 to xk are all my training instances from here to here. They are all my training instances, okay, where I'm going to identify that are nearest to xq. So what we did, we had all of these training data and I had my testing data. I created one more table, right? One more table identifying the Euclidean distances of this. So I had written data point 1, 2, 3 and 4. I think I remember we had 4, 5, 3 and 3.6 was the value. And we actually gave them the rank for that also, 1, 2, 3 and 4. Okay. So which they're telling is x1 to xk are the instances that is there. Now for each and every instance, I have to calculate the Euclidean distance from so and so. That is what I have done in this table. xq is this test data. From here to the given data, I calculated and the value of that was 4. From here to the second was 5. From here to the third was 3. From here to the fourth was 3.6. So I've calculated all the 4 values of it. So once I finish that, I have to give a rank to it, or I have to identify, okay, how well it is going to get classified, right? So in order to do so, what I will tell is x cap of fxq is equal to, or this is basically, it will give me the argmax of v belong to capital V, okay, it is in the version space, summation of I is equal to 1 to k delta of v comma x of f of xi. So it is very simple and very easy. I just want you to keenly observe what we are doing. See, I want to take up this. What is f of xq? If I have to consider my previous example, xq is my this. I want to make sure that when I consider this, I wanted to know which class does it belong. That is my basic question. And I'm going to tell, okay, xq belongs to a class. How do I get to know that? Taking the argmax of what? Each and every thing, every instance that I take up with the version space. Yes, I consider the version space because I want to make sure that lies within this. From summation of 1 to k, some summation of 1 to k is all of these 4 instances. Yes. Delta of v comma f of xi, okay. Delta of v is what? V is that particular instance. F of xi is the data. So it is telling, in this table we had three values. If you remember, in the table we had 3 values. When I told the rank of this is 1, when I told the rank of that is 1, which means that I used to take the third attribute of it, the similar third attribute of it, and it was telling me that the value was good. Yes. Again, I took the fourth attribute of it and the value of it was good. I took the first attribute, the value of it was bad. Okay. So this entirely, the instance whatever I was considering, is my delta V of f of x. Take the argmax of delta V of f of x, which is B, G and G. That is my first data type, the third and the fourth instance. So these value, take the argmax of it. Argmax of it is basically 2 over here and 1 over here. Anything that was major was good. So that good value is going to be placed over here. So f cap of x of q is equal to argmax of v belongs to capital V, summation of I is equal to 1 to k, delta of v of f of x. I'm trying to correlate everything with respect to this example. I want you to visualize it so that it is going to be very easy for you for your understanding. Please let me know if you have any doubts here. Each and every step is very clear over here. It's telling when I have to train it, I'm going to consider each and every instance and I put it into my training data. When I'm going to classify it, I have a query called as xq, which is nothing but my test data. From the test data, I have to identify the distances or Euclidean distances with all of its training data. All the training data is from x1 to xk. In case here we had the first data type, second data type, and the third data type, fourth data type. So these are my instances. So with particular instances, I have the durability, I have the strength, and the final, the class value. Now what is telling? For xq is basically my test data. I have to identify to which class does it belong. That is basically a function. Identify the class that this xq belongs to. How do I get to know that? I consider the argmax of what? Because I performed the calculation of this Euclidean distance and I ranked my data. From the ranked data, I checked out which data type has the smallest value, right? So from that smallest value, what did I do? I correspondingly took its entire instances and the class value of it. Along with it, a similar again for the second instance, and for the third instance, I took the same thing. From here, I am going to consider the argmax value because it has 2 here and 1 over here. 2 which is higher, majority of votes are good. So which means that this entire class will become good. So identifying each and every such value of it is basically, we consider it given by the function called as lambda v comma f of x. With respect to I. With respect to I is nothing but this value. When I is equal to 1, I'll get this. When I is equal to 2, 3, 4, I used to get these values, the final class value. So when I perform that, I'm going to take the argmax of 2 or 1. 2 is bigger. The value of that is good. I'm going to give class is equal to good. So this is completely about your algorithm with respect to k nearest neighborhood. Please let me know if you have any queries here. If not, I'll go ahead with the next topic. Can I go ahead?
Yes.
Okay. So basically the algorithm, it's robust to noisy data. It is suitable for large sets of training data. It is highly effective inductive inference model, and the classification can be easily understood by the bias or the majority number of votes that we give over here. Okay. So this is completely about your KNN algorithm. So let me go ahead with the next topic of it, so which we call it to be as the radial basis function. So radial basis function. Where have we heard this term radial basis function? Somewhere we should have heard about this, right? We should have heard about the radial basis function. Where have we heard? Please recall. There's a lot of network issues, guys. I don't know, it's reconnecting again and again. Let me see if that is the case, then I'll start to scan it and display it. So it's RBF. Remember, where have we seen? Am I audible? Guys, am I audible? Guys, am I audible? Am I audible? So it's basically a Gaussian curve. It's a Gaussian curve. So you can see that. How does a Gaussian curve look like? I just wanted to interpret the previous one with this. I just take the white color. Okay, yeah, white color. See, radial basis function is basically, when I tell a Gaussian curve, it's basically Gaussian data points. Radial basis itself, which means that it is a set of Gaussian data points, and the curve looks like this. If you remember, we had a curve like this, a bell curve, where we told that the center of it is basically the mean, and then we have the standard deviation from the distances from the mean to the particular data point, right? So this is how our Gaussian curve used to look like. But let me start representing that with respect to a data points, a set of data points, okay? So let me consider the center of it is basically a mean. I have certain data points like this, anywhere which is scattered, okay? Or I'll just write it random. Even if I take a graph like this also, so basically in the graph, if I consider this center data point to be as the mean, the first point, okay? If I have to identify the distances of that, right, basically for visualizations, you can check out that, okay, whether this will form, this point will form one curve. There will be a priority given to this. What is the distance from here to here? The next, the points which are lying on the second curve, points lying on the third curve, points lying on the fourth curve, points lying on the fifth curve. So when I look at this something, when I start visualizing it in a 3-dimensional or a 2-dimensional picture, right? Any data point which is lying over here, okay, will have a distance from here to the, so which tells that object is actually far away from it. So I can consider that to be as the radius function, okay? So normally, however you consider the Euclidean distances now, right? This radial bias function is basically used in many of the models, okay? So it is basically used in the neural network structures when we consider neural network one step ahead, okay, from the k nearest neighborhood, whatever we have seen, or k means or something. Now we are going a next step ahead to the neural networks. How does the same concept that we are doing it with respect to k means or excuse me, I'm sorry. So either with k-means or k-nearest neighborhood, we identify the distances between the Euclideans, okay, and we do it, right? Okay, how is this slightly and improvised with respect to neural networks? So radial basis function with respect to neural networks are conceptually similar to the KNN models, okay? The basic idea is that the predicted target value of an item is likely to be about the same as the other items that have close values of the predictor values, which means that when I consider, okay, let me just start interpreting this with a different color so it is easy for you to understand. Okay, so suppose let me consider there's a point over here, okay. The way in which I identify that point, okay, with respect to the predictor value, suppose let me consider this the predictor value, okay, the way in which how far is that object with respect to the given data matters a lot. And this basically, the distances that I observe here is going to be the radius function. When I consider, see, this is the Gaussian one, the same representation when I look it from the above. So let me consider I'm looking it from the above. When I look it from the above, there are circles that has been created over here like this. When you look it from the above, try to imagine yourself, please. When you try to look it from the above, you can see the circles. That representation, the top view of it is what I've shown you over here. Okay. So which means that from this center point, okay, where exactly the point is lying, the distances, how far the circles are. Okay. So which means that from that mean value or from the value that I consider, remember every time in k means, we were identifying the mean and we were updating the mean values, right? If you remember that, okay. So here it is basically going to be the radius of the circle. So the radial basis function is named because the radius distance is the argument to the function where we take the weight to be the distance. Okay. So it's seriously a simple analogy with respect to the ones that we have discussed with k-means or k-nearest means. Here I'm just trying to show you, okay, how it varies with the Gaussian points, and with the Gaussian points, how does the top view of the Gaussian points look like? And that's why I thought it will be helpful if I put it out in the pictorial representation like this. How far the distance is from the center point? So far we can consider that it is away from us. So I can consider it, okay, give a weightage to it. And I tell you, okay, since the point is so far, which means that I'm going to consider only the nearest points of it, which lies it within this circle or the next circle or whichever the one that I wanted to identify. So it takes the priority of the data points by considering the radius value of it. Okay. So I'm just trying to clear the screen. So it was being developed, or it was being coined by Pavel in 1987, Bromhead and Lowe in 1988, Modi and Ducker in 1989. Okay, so they actually learned all the hypotheses. It's basically whatever we tried to we came up with how exactly we have to select the hypothesis. Okay, how are the data points are plotted within the given graph that was. So based on all of those assumption values, they came up with a function of the form, which is something like this, which tells you that I have a particular weight of it, which is W0, which is my bias. Summation of u is equal to 1 to n. You can consider the WU is the weight, K is the actual values of it, and D of XU comma X. So the representation of that is basically what I'm going to give you over here. So let us consider the neural network structure to clearly give you an idea of what I'm talking about. So if I consider the neural structures, my structure is here. Okay. So this is my f of x function. F of x is my function. Okay. For f of x to happen, I have a weight which is W0. Please compare it with your artificial neural networks. Okay. So I have 1 is my weight W0. What I used to do, W0 plus W1 into X1. X1 is over here with respect to these values. Okay. W1 is the weight of this, and I have each and every neural network with a radial basis function. Initially, when I tell a neural network, I used to have two parts with this, right? The first part is the summation of it, which I perform. The second part is the activation function. Normally, the activation function, I used to take a sinusoidal curve. But here, when I tell I'm going to consider a neural network with respect to radial basis function, the function that I'm going to consider is going to be a bell curve, the Gaussian data points bell curve. Okay. So each and every value of that, I'm going to represent it with a Gaussian curve. Okay. So it's the same. W0 is my bias, W1 into X1, W2 into X2, so on up to Wn into Xn will become my summation. The summation of that value, I'm going to pass it with respect to the radial basis function, and again from there I will have all of them interrelated to get over here. Maybe here I might have one more summation of it and a pre-activation function. If I again have a pre-activation activation function, so this is pre-activation function, the summation. The output value, if it has an activation function, maybe I can have a sigmoid function or a sine function or anything that finally gives me an output. Okay, so this is basically two main very important points to note over here is I'm going to identify first thing how exactly the distance of that particular mean value with respect to the given data point is being considered using the radial basis function, where it gives a lot of weightage to the radius function, where I'm going to represent a form of a bell curve and its particular distances. Okay, that's the first point. The second point is whenever I tell the radial basis function is with respect to the neural network, the pre-activation and the activation function that I'm going to consider is basically the summation with respect to all the input value into its weights. That is the first point. That's my pre-activation function, and my activation function is all the time basically going to be the radial basis function. So the same thing is what I'm going to represent over here. Okay, if you just consider the same thing is what I'm going to represent it over here. W0 plus WU into XU. This is basically WU into XU, and DU, you have here DU XU into X. Okay, so basically where each XU is an instance from X and where the kernel function KU is defined so that it decreases as the instance d of XU comma X increases. So there's one slight thing that you have to consider here. You can see here the kernel function is defined as that it decreases. Okay, it decreases as the distance of this increases, which means that when I consider a point like this, okay, I have to tell you this, which is very important. So suppose I consider the value of this. Okay. The value of the kernel function decreases because it means that it is very close to this. The value of this actually decreases because it is close to this. When I tell the value of this one, when I consider the data point of view, the value of this increases as it is far away from the particular data point. As simple as that. The value of the kernel function is defined so that it decreases as the distance of this. So when the data point goes farther and farther, which means that the distances of it is more. When it is farther, which means the kernel function will have a lesser value for that. Okay, so this is about your kernel functions, and normally we know how do we represent the bell curve as 1 divided by 1 plus e to the power of 1 by 2 sigma square u into du. This is basically mean minus of variance difference. D square is basically the variance. So we normally write it right. 1 e to the power of sigma square into mu minus or xi minus of mu the whole square. A same function over here. We are writing, representing it over here. So this is about your radial basis function. If you have any doubts over here, let me know. Joycey seems to be too tensed. Any doubts here?